Welcome to the Deep Dive, the show where we cut through the noise and get straight to the insights. Today, we're going to marvel, I think, at the current state of artificial intelligence. I mean, think about it for a second. We have systems like GPT-4, right, which can generate human-like text. So fluid, so convincing, sometimes it's hard to tell it's not human. And then there's AlphaGo Zero, Mastered Go, that incredibly complex game with no human training at all, inventing totally new strategies, even that groundbreaking style of play. It often feels a bit like magic, doesn't it? Like these things just appear fully formed. But the truth, as always, is more complicated. They really stand on the shoulders of decades of scientific inquiry, relentless engineering, and actually a surprising amount of perseverance, often in the face of, well, real skepticism. Our mission today is to take a deep dive into what we're calling the Connectionist Legacy. This isn't just about the latest shiny object. It's the fascinating, sometimes kind of tumultuous story of how neural networks, this idea that was once ridiculed, widely dismissed, became the defining paradigm of modern AI. We're going to trace their journey right from the earliest inspirations, which were deeply rooted in biology and the human brain itself, through the fundamental learning rules that make them tick, past those periods of intense skepticism, even outright rejection, what people call the AI winters, and finally land on the AI explosion we're all witnessing right now. And what's truly remarkable, maybe the most important lesson here, is how even the failures, the perceived dead ends, taught these invaluable lessons. They acted like catalysts, really paving the way for the sophisticated, adaptive AI we interact with daily. To guide us through this intricate, often cyclical history, we're unpacking a really rich stack of sources. We'll be drawing from foundational texts like Perceptrons by Minsky and Paper, the groundbreaking parallel distributed processing volumes, and the big deep learning textbook. And we'll weave in modern insights too from works like Human Compatible AI, AI 2041, and Architects of Intelligence. These documents taken together give us the historical context, the technical evolution, and the profound current implications of these connectionist ideas. So for you, the curious learner, this deep dive is really for anyone who wants to understand the why and the how behind AI's, well, frankly, remarkable evolution. Expect surprising facts, hopefully clear explanations cutting through the jargon, and insights into how just sticking with a research idea, even when it's unpopular, can lead to monumental breakthroughs. So let's get into it.
It really is an incredible story, a story of scientific resilience,
Yeah.
and a testament to the power of a fundamental idea. What's often overlooked, and what I find fascinating, is how those core ideas, even when they seem to hit a wall, they never really vanished. They just evolved and kind of went underground, waiting for the right compute power, the right data, the crucial algorithmic tweaks to bring them into their own, to let them really flourish.
It really is like a long-form historical drama playing out over decades. Okay, so let's dive into the opening act. Let's go back to the very beginning. The dawn of connectionism, brain-inspired beginnings. This is where that initial spark for AI, specifically for neural networks, really ignited, and often with these grand, almost philosophical goals.
Indeed. Early visions. Simulating the brain really does set the stage for everything that follows. The core idea, in its simplest form, was almost disarmingly intuitive, but also incredibly ambitious. If we could just figure out the fundamental ways our neurons connect and learn, then surely we could replicate that intelligence in a machine, maybe even surpass it. The inspiration was purely biological, looking inward, right, to our own minds for the blueprint of artificial minds.
And the ambitions were huge right from the get-go. Early computer scientists weren't just thinking about faster calculators. They dared to imagine machines with brains way more powerful than ours. One source even asks if an artificial mind, once we really understood human mental machinery, could make Aristotle look like Homer Simpson.
Laugh slightly. Yeah, that's quite the image.
It is. Comparing a foundational philosopher to a cartoon character, it just speaks volumes about the sheer audacity, the ambition to not just replicate, but potentially vastly exceed human intellect.
It really does. And this bio-inspiration, it provided this incredibly powerful metaphor, albeit maybe an oversimplified one sometimes, for thinking about learning and processing information. It suggested intelligence wasn't about one central brain directing everything, but maybe a vast distributed network, simple components working together. This shift in thinking away from a single CPU was just foundational.
Okay, so with these grand brain-inspired visions floating around, the critical question became, how do these basic neurons actually learn? How do they form connections? And that's where we hit a really foundational concept, often summed up as Hebb's learning rule, the foundation of association, that famous phrase, neurons that fire together, wire together. Why was this rule so profound for understanding how networks could learn?
Well, Hebb's rule proposed by Donald Head back in 1949, is, elegantly simple. But it laid critical theoretical groundwork for connectionist learning. It basically posits that the strength of connections, what we now call weights between neurons, increases when they're simultaneously active. So imagine two neurons, A and B. If neuron A consistently fires just before or at the same time as neuron B, the connection between them gets stronger. That makes it easier for A to activate B in the future. And mathematically, this is exactly what we see in models like the autoassociator described in parallel distributed processing. The weight change is directly influenced by the product of the input and output unit activations. So yeah, the more they're active together, the stronger the link. They form an association.
So essentially, this rule allowed these systems to build their own internal logic based on experience. Instead of having every single connection planned out in advance, that seems like a radical departure.
Oh, absolutely. This simple yet profound rule provided a concrete, biologically plausible mechanism for learning associations and patterns, core parts of intelligence. It offered a path for systems to adapt to change based on what they encounter without needing explicit hand-coded instructions for every single scenario. It was a theoretical breakthrough. It showed how memory and learning could just emerge from simple, local interactions between these units.
And building on that theory, we started seeing actual machines. The perceptron, a pioneering step. Frank Rosenblatt's perceptron, late 1950s. One of the first explicit working examples of these connectionist ideas. What was it designed for, and why was it such a big deal back then?
The perceptron was a simple, single-layered neural network, designed mostly for pattern recognition, specifically classification tasks. It was a tangible example of a learning machine. And that, at the time, was truly revolutionary. It could learn to classify data that was linearly separable. Now, what does that mean? Imagine you have two types of data points on a graph, maybe red dots and blue dots. If you can draw one single straight line, or maybe a flat plane in higher dimensions, to perfectly separate the red from the blue, that data is linearly separable.
Okay, so it could draw a line between two categories.
Exactly. And the famous perceptron convergence theorem stated that if the data is linearly separable, the perceptron learning procedure is guaranteed to find that separating line eventually. This was a huge early step. It showed a machine could actually learn a distinction just from examples. Not programmed rules, but learning.
So it could learn to tell the difference between, say, two different letters or shapes just by being shown examples. That's pretty impressive for the 50s. It wasn't just following rules, it was learning to discern patterns.
Precisely. A pivotal early step. Showed a machine could adapt its internal parameters, those connection weights, to perform a task. It laid the groundwork for so much of modern machine learning, and understandably sparked immense excitement about where AI was heading.
Right. So from this exciting start, the perceptron showing real promise, it must have felt like intelligent machines were just around the corner. But, history rarely moves in a straight line. Often the biggest leaps forward come after hitting some really tough roadblocks. And for connectionism, that roadblock came with a powerful mathematical critique, ushering in what many call the first AI winter challenges and setbacks. This period was a major reality check.
It really was. The initial buzz around perceptrons eventually met some serious academic scrutiny. Minsky and Papert's critique on veiling limitations was particularly influential. Their 1969 book, Perceptrons, wasn't just a casual dismissal. It was a deep, rigorous mathematical analysis of the limitations of these single-layer networks.
And their findings were pretty devastating for the field at the time, weren't they? They basically showed these promising networks couldn't solve some fundamental problems that felt essential for any real intelligence.
That's exactly right. Their work demonstrated that these simple, single-layer networks just lacked the expressive power for many complex tasks, specifically anything that wasn't linearly separable. They showed, for instance, that a diameter-limited perceptron couldn't solve a relatively simple problem, determining if a binary image is simply connected.
Simply connected, like, is it one solid shape or does it have holes or separate parts?
Basically, yeah. A single-layer perceptron couldn't reliably tell if a shape was one connected blob or had holes or multiple pieces, especially if those pieces were far apart. More broadly, their analysis concluded that solving these general predicates required perceptrons of unbounded order, which basically meant you needed networks far more complex than the simple single-layer designs they were looking at. It was a profound insight, even if it hurt at the time. Simple, single-layer networks just couldn't capture the world's complexity.
And what's interesting is how this critique wasn't just theoretical. It had this real psychological effect on the research community. It hit funding. It changed the direction of AI
Oh,
research.
definitely. It was a significant obstacle because, as they pointed out, it brought the discussion into contact with classical mathematical methods of proven depth. It brought a feeling of real mathematics to the field, contrasting it with what they called purely combinatorial methods. This mathematical rigor highlighted a fundamental architectural flaw, and it significantly dampened the enthusiasm. Many started thinking neural nets were just a dead end.
Oh, in hindsight.
In hindsight, this critique, while seemingly devastating, actually laid the intellectual groundwork for what we now call deep learning. It pushed researchers eventually to think beyond simple linear boundaries toward multi-layer, nonlinear architectures needed for complex problems. It wasn't a stop sign, it was a sign saying need more power.
And this critique, along with other factors like maybe overpromising early on, led directly into the AI winter, a shift away from neural networks.
Yeah.
What was this period like? How big was the shift?
The limitations exposed by Minsky and Papert, plus the fact that early AI just wasn't delivering on some of the grand promises, machines just weren't smart enough yet for the tasks envisioned, really fueled this first AI winter. It hit its stride around the mid-1980s. Funding dried up. Interest in neural networks just plummeted. Stuart Russell gives a great example in Human-Compatible AI. He says his AI course at Berkeley, which now has over 900 students, only had 25 students back in 1990.
Wow, 25. That's a stark difference.
Yeah, he puts it plainly. The second AI bubble burst when these systems proved to be inadequate. Again, the machines just weren't smart enough. An AI winter ensued. It wasn't just a cooling off, it was a deep freeze for connectionism, pushing it to the margins.
So if neural networks were mostly out, what became the focus? Where did researchers put their energy?
Well, the focus largely shifted to what we now call symbolic AI. This approach emphasized explicit rules, logic, knowledge representation, trying to build intelligence by programming in human-like reasoning processes directly. They thought this was a more promising path, maybe more transparent, more controllable. This era really stressed the need for smarter, more robust AI, and it pushed the field to become far more mathematical, but in a different direction, away from those brain-inspired models.
It sounds like a really tough time for anyone who still believed in that connectionist vision. But even during this winter, some ideas didn't completely die out. They kept simmering, right? Like sustained ideas, the brain state in a box.
Yeah, exactly. Despite the general downturn and the shift to symbolic methods, some connectionist research continued, often in quieter corners, specific niches. J. A. Anderson's brain state in a box model is a good example. It was described as a close relative of the simple linear associator, like the perceptron, but crucially, it aimed to tackle the weaknesses of purely linear systems. How? By adding nonlinearities, like linear threshold units. These nonlinear elements meant the system wasn't just stuck drawing straight lines to separate data. It could start learning more complex, curved boundaries between categories.
So adding these nonlinear parts was a clever way to try and get around the very limitations Minsky and Papert had pointed out for linear systems, even if the mainstream wasn't really listening then.
Precisely. These efforts, though maybe less visible and less funded, were quietly building the mathematical foundations and architectural ideas that would prove absolutely crucial later on. It showed the persistence of that core belief in neural networks. Research continued, keeping that flame alive, even when the wider community had largely moved on. It was a period of quiet, sustained effort.
And thankfully, that long, cold winter didn't last forever. Eventually, the scientific ground started shifting again. New tools, new understandings emerged. Which brings us to the resurgence probabilistic reasoning and parallel distributed processing. This is where we start seeing the seeds of the modern deep learning era really start to sprout.
Absolutely. A really critical turning point came with the growing realization that the real world is just inherently uncertain. It's messy, ambiguous, purely logical reasoning, the kind favored by symbolic AI, just couldn't cope well with that ambiguity. Integrating uncertainty. Probability theory in AI provided a powerful, much more flexible framework for dealing with these real-world complexities.
So the reliance on absolute black and white logic, the hallmark of symbolic AI, was actually proving to be a major limitation for building truly adaptive systems.
Exactly. As human-compatible AI notes, logic requires certainty, and the real world simply doesn't provide it. Think about understanding language or recognizing an object in a photo. These tasks are full of probabilities, likelihoods, not rigid if-then rules. Judea Pearl, a Turing Award winner, was a key figure here. He pioneered methods for uncertain reasoning based in probability theory, developing things like Bayesian networks. Gradually, AI researchers started adopting Pearl's ideas. They embraced probability theory, utility theory, and this connected AI to other established fields like statistics, control theory, economics. This change, as some observers note, really marked the beginning of modern AI because it allowed AI to move beyond brittle, rule-based systems to more robust systems that could actually reason effectively under uncertainty.
That sounds like a massive shift, connecting AI to this much broader scientific and mathematical foundation, grounding it in the reality of how information works in an uncertain world.
It was absolutely pivotal. It gave AI the mathematical toolkit to handle the inherent messiness of reality, rather than forcing problems into overly simplified logical boxes.
Okay, so with this new probabilistic toolkit and the quiet persistence of those connectionist researchers, the ideas that had been simmering finally started to boil over into a new, powerful movement. Parallel distributed processing, PDP. A new paradigm emerges. The 1980s saw this really come to the fore.
Yes, PDP models emerged as a direct counterpoint to symbolic AI, drawing heavily on that original biological inspiration. They champion the idea that intelligence doesn't come from explicit rules or symbols, but from the interaction of many simple interconnected processing units working in parallel. The influential Parallel Distributed Processing book describes this set of processing units where intelligence is an emergent property of their collective distributed activity. A key emphasis was on distributed representations. Concepts aren't localized in a single one-unit, one-concept way, like in some symbolic systems. Instead, a concept like cat is represented by a pattern of activity across many units.
So instead of one neuron firing for cat, it's a whole pattern across many neurons, each contributing a little bit. What's the advantage of that?
Well, it makes the system more robust. If one unit fails, the whole concept isn't lost. And it allows for much richer representations of nuances and relationships between concepts. They also focused on using differentiable activation functions. Unlike the sharp on-off thresholds of early perceptrons, these allowed for smoother, more gradient-based learning, which turned out to be crucial.
And this distributed approach allowed for more subtle processing.
Yes, much more subtle, context-dependent processing. Things like semantic constraints, how a word's meaning is shaped by the words around it, or the integration of featural information in speech perception, were explored using PDP models. It showed they could handle nuance, ambiguity, context in ways symbolic systems often struggled with. It was a compelling alternative, suggesting complex cognition could emerge from simple parallel interactions, much like we believe happens in the brain.
It's fascinating how that distributed brain metaphor became central to a successful computational model. Now, to handle more complex data types, like sequences think language or time series data, new architectures were needed. That brings us to recurrent neural networks, RNNs, processing sequences.
Right. To process sequential data, like speech, text, or even video frames where order matters, recurrent neural networks, or RNNs, were developed. Their key innovation was allowing information to persist over time within the network. They have connections that loop back on themselves, creating a kind of internal state or memory of previous inputs. Unlike a feed-forward network that just processes each input independently, an RNN's output depends not just on the current input, but also on what it has seen before. This is often achieved through parameter sharing for the weights used in the recurrent connections. The same weights are applied at every time step. This lets the network apply learning from one part of a sequence to other parts, building context over time.
So they essentially have a memory that lets them understand context over time, which is obviously critical for things like language comprehension or predicting the next word in a sentence. But I gather these early RNNs had their own significant problems, especially with long sequences.
Oh, definitely. Despite their conceptual elegance, early RNNs suffered badly from problems like vanishing gradients or sometimes exploding gradients, particularly when dealing with long sequences. Imagine trying to pass a message down a very long line. With vanishing gradients, the signal gets weaker and weaker with each step until it's basically lost by the end. The network forgets things from the distant past.
So it can't connect the beginning of a long sentence to the end.
Exactly. And with exploding gradients, the opposite happens. The signal gets amplified uncontrollably, becoming distorted and overwhelming the network. This made learning long-range dependencies extremely difficult. The solution, a major breakthrough, came with gated architectures like LSTM, long short-term memory, and GRU, gated recurrent unit. These introduce gating mechanisms, essentially, smart switches that allow the network to selectively forget or retain information over long periods, mitigating the vanishing gradient problem.
And this wasn't just a small tweak, was it? LSTMs and GRUs were a huge deal. The key insight seems to be that memory needs control, not just connections, but these intelligent gates deciding what information flows through.
Precisely. These weren't just incremental improvements, they were fundamental algorithmic advances. They transformed what RNNs could do, unlocking their potential for tasks requiring understanding of complex, long-range temporal relationships. They powered major breakthroughs in language modeling, machine translation, and more.
And those algorithmic advances, combined with other factors like just massively more computing power and enormous data sets, really launched us into the deep learning revolution scaling and sophistication. This is the era that truly brought AI into our daily lives, often without us even noticing.
Absolutely. The ability to train much deeper, more complex networks was the game changer. Deep networks and backpropagation was utterly central to this. Backpropagation is the algorithm that provided an efficient way to train these multi-layer networks. Before backprop, training networks with more than, say, one or two hidden layers was computationally almost impossible. It uses the chain rule from calculus to efficiently figure out how much each weight, each connection in the network contributed to the final error. Then it propagates that error information backward through the layers, allowing each weight to be adjusted slightly to improve performance.
So backpropagation was the key that unlocked the ability to actually train these deep networks effectively. Without it, they were just complex structures that couldn't really learn.
Pretty much, yeah. It efficiently calculates the gradients needed for optimization, allows for those fine-grained adjustments layer by layer, the ability to also do partial optimization using linear methods for the final layer weights helped improve efficiency too. But backprop was the critical enabler for training networks with many hidden layers. It allowed them to move far beyond the limits of single-layer perceptrons, learning complex nonlinear relationships and hierarchical features built on top of other features. It was really the engine that made deep learning practical.
Okay, so once deep networks could be trained, researchers started designing specialized architectures for specific types of data. Convolutional neural networks, CNNs, visual breakthroughs completely changed computer vision. How machines see.
CNNs were ingeniously designed. They build in certain invariance properties directly into their structure, which makes them incredibly effective for image data. They use two main tricks: local connectivity, where each neuron only looks at a small patch of the input image, like receptive fields in our own visual system, and parameter sharing. Parameter sharing means the same set of weights, called filters or kernels, are slid across the entire image. This allows the network to detect a feature, like a vertical edge or a specific texture, no matter where it appears in the image.
So a detector for, say, a cat's ear can find that ear whether the cat is in the top left or bottom right of the picture.
Exactly. That's translational invariance. This approach was widely applied to image data, famously for recognizing handwritten digits. A filter designed to detect a curve can find that curve anywhere.
I remember seeing those demos of CNNs reading handwritten zip codes for the post office with amazing accuracy. It felt like a machine that could actually read, handling all the variations in handwriting.
It was a powerful demonstration. A network called Net5, for example, achieved error rates around 1.6% on those ZIP code problems, much better than simpler networks. It proved the practical value. And the design showed that subject matter knowledge, like the fact that features should be detectable anywhere, can and should be used to improve their performance. It wasn't just brute force, it was smart architectural design inspired by vision. CNNs really showed how features of, say, handwriting style should appear in more than one part of a digit. It was the first time AI truly excelled at visual perception tasks.
Okay, and that brings us pretty much right up to today. The incredible advances in large-scale AI that are fundamentally changing everything. Scaling and transformers, the LLM era. This is where we see models with these almost spooky emergent abilities, doing things that seemed like science fiction just a few years back.
Indeed. The last few years have seen just an explosion in the scale of neural networks. This has led to these emergent abilities we see in large language models, LLMs like GPT-3, GPT-4, PaLM-2. The transformer architecture has been absolutely central to this. Transformers rely heavily on a mechanism called self-attention. You can think of it like this. When the model processes a word in a sentence, self-attention allows it to look at all the other words in that sentence simultaneously and figure out which ones are most relevant for understanding the current word's meaning and context.
So for the word bank in I went to the bank by the river, it can figure out from river that we mean a river bank, not a financial institution.
Precisely. It weighs the importance of different words for contextualizing each specific word.
And then there's multi-head attention. What does that add?
Multi-hit attention takes it a step further. It allows the model to learn several relevant pieces of information for a given word by running the self-attention mechanism multiple times in parallel, each focusing on different aspects or subspaces of the information. It's like having several spotlight teams simultaneously looking at the sentence from different angles to build a richer understanding of each word's context. This, combined with just massive scaling going from millions to billions of parameters, has been transformative. OpenAI's GPT-3, for instance, showed it could reply to just about any query with plausible human-like text, composing poetry, writing code, answering questions, and now GPT-4 and PaLM-2 are showing machines surpassing humans in many cognitively demanding tasks. This is where those emergent abilities really start to pop.
You keep mentioning emergent abilities. Can you give a concrete example? How does a model suddenly do something it wasn't explicitly trained for just by getting bigger?
It's one of the most fascinating and very slightly mysterious aspects right now. Emergent abilities are capabilities that aren't really present in smaller models, but they just sort of appear once a model hits a certain threshold of size and training data. It's like a phase transition. For example, techniques like tree of thoughts, or REACT, which stands for reason and act, seem to emerge in large models. They allow the LLM to break down complex problems, explore different reasoning paths, backtrack, even self-correct errors. Essentially, they start planning their actions and thoughts in ways that weren't explicitly programmed but emerged from the scale. They can suddenly generate novel solutions, perform multi-step reasoning, write functional code for tasks they've never seen, simply because they're so big and have processed so much data.
Wow. So it's not just doing the same things better, it's starting to do new things.
Kind of, yeah. Ray Kurzweil predicts AI will pass the Turing test by 2029, largely because of this rapid scaling and the unexpected capabilities it unlocks.
That's incredibly soon. It really highlights how powerful these scaled models have become, almost shifting our definition of machine capability.
This scaling, combined with architectural innovations like the transformer, has just unlocked unprecedented capabilities, especially in language. It fuels the idea that maybe simply making models bigger and training on more data will eventually yield very powerful general AI. Those emergent abilities are a direct result of this massive leap.
Okay, so far we've mostly talked about pattern recognition, seeing images, understanding text. But AI isn't just about perception. It's also about learning how to act in the world, how to make decisions, achieve goals through interaction. That brings us to learning through interaction reinforcement learning's role.
Correct. Beyond supervised learning, learning from labeled data, early reinforcement learning, learning from trial and error emerged as another really powerful paradigm. This is all about agents learning optimal behaviors through trial and error interaction with an environment. They take actions, see what happens, and get rewards or penalty signals telling them if the action was good or bad towards achieving a goal. Think of a robot learning to walk or an animal learning a maze.
This sounds much more like how we or animals learn naturally, right? Trying things, seeing what happens, adjusting based on whether the outcome was good or bad. Was that the inspiration?
Absolutely, it's heavily influenced by that. Early work on things like temporal difference learning, or TD learning, was deeply influenced by animal learning theories and concepts from behavioral psychology, conditioning, rewards. Richard Sutton, a key pioneer here, took an important step in 1988. He separated temporal difference learning from control, treating TD learning primarily as a general method for predicting future rewards without necessarily needing a perfect model of the environment.
So the focus shifted from just identifying patterns in static data to making sequences of decisions in a dynamic world where the payoff for an action might not come immediately.
Precisely.
Mm.
It's crucial for agents that need to operate in dynamic, interactive environments where consequences unfold over time.
Hmm.
It's about learning through active exploration, not just passive observation.
Now, to make reinforcement learning work better, especially in complex scenarios, a clever architecture came about. Actor-critic architectures combining prediction and control. How do these work? What problem did they solve?
Right? Actor-critic methods were developed to make RL more efficient and stable. They cleverly split the learning task into two complementary parts, kind of like, well, an actor and a critic. One component, the actor, is responsible for learning what actions to take. It learns the policy. It's the performer. The other component, the critic, learns to evaluate how good those actions or the resulting states are. It learns a value function, essentially judging the actor's performance. This approach was applied early on to classic control problems like Mitchie and Chambers' pole balancing problem, learning to balance a pole on a moving cart. Sutton studied it extensively in his PhD thesis in '84, and then Anderson's PhD in '86 significantly extended it by using backpropagation neural networks for both the actor and the critic, bringing deep learning representations into the mix.
Ah, so you have one part deciding what to do and another part giving feedback on how well it did. That sounds like a much richer learning signal than just a final reward.
It is. The critic provides a more immediate and informative signal, helping the actor learn faster and more effectively, especially when combined with the power of neural nets to represent complex policies and value functions. It leads to more sophisticated and stable learning in complex, long-horizon tasks.
And the culmination of all this RL work, especially when combined with deep neural networks, deep RL, is behind some of the most stunning AI achievements we've seen recently. AlphaGo and beyond reinforcement learning's impact today.
Oh, absolutely. Modern deep reinforcement learning has produced extraordinary results, often achieving superhuman performance. The prime example everyone knows is DeepMind's AlphaGo. Back in 2016, it defeated the human world champion at Go, a game vastly more complex than chess. AlphaGo famously invented a groundbreaking new style of play. Remember Move 37 in Game 2 against Lee Sedol? It was so alien, so outside human intuition, commentators thought it was a mistake at first.
I remember that. It felt like a moment where AI wasn't just mimicking humans, but discovering something genuinely new.
Exactly. It showed AI's potential to find creative strategies beyond human understanding. And then AlphaGo Zero took it even further. It achieved superhuman ability without human training at all. It just started with the rules and learned entirely by playing millions of games against itself. Pure self-play, self-improvement, a powerful demonstration of RL's potential.
And RL isn't just for games anymore, right? It's being used elsewhere.
Definitely. It's used in robotics, optimizing complex systems, even things like neural architecture search with reinforcement learning, where RL helps design better neural network structures automatically. And crucially, it's used for fine-tuning language models. Techniques like reinforcement learning with PPO, proximal policy optimization, are key to what's called RLHF reinforcement learning from human feedback. This uses human ratings of LLM outputs as a reward signal to reinforce the model, generating more helpful, harmless, and honest responses. It's shaping the behavior of the models we interact with.
That's fascinating. So RL is now helping to align these incredibly powerful language models with what we actually want them to do using our feedback as the guide.
Yes. These successes show RL's power to discover novel strategies, generalize, and even help align AI systems, extending connectionist principles into strategic reasoning, decision-making, and human-AI interaction.
What an incredible journey we've mapped out. From those earliest brain-inspired concepts like Hebb's rule and the perceptron, through the tough times of the AI winter that forced a crucial rethink, to the resurgence with PDP, deep learning, reinforcement learning. We've seen how ideas once dismissed as impractical, even impossible, have become the very foundation of the AI revolution we're living through. Which brings us to the enduring legacy connectionism's triumph and future. It really is a story of persistence and a remarkable scientific comeback.
It truly is. And from ridicule to defining paradigm perfectly captures that arc. Connectionism, once nearly abandoned, is now undeniably the dominant force in AI. Those decades of trial and error, the failures that, as the sources say, taught valuable lessons, they weren't roadblocks. They were essential parts of the process. It wasn't a straight path at all. It was winding, full of hard-won insights.
It's such a powerful reminder that failure in science is often just learning. The critiques, the limitations identified by Minsky and Paper, they were actually vital signals pointing the way toward what was needed next. Deeper networks, better algorithms.
Exactly. As one source puts it, the AI community learned its lesson. Smarter, obviously, was better, but we would have to do our homework to make that happen. That homework involved developing deeper architectures, backpropagation, rethinking representations, and crucially, as another source notes, the seeds of today's progress were sown during that AI winter. It highlights that cyclical nature of science, the importance of fundamental research even when applications aren't obvious, that blend of biological inspiration, mathematical rigor, and eventually massive computational power. That's what ultimately proved connectionism's strength and let it rise again.
And speaking of computational power, that leads directly to the power of data and scale. Modern connectionism's success is just inseparable from things that early pioneers simply didn't have. Massive data sets and the compute power to train enormous models on them.
Oh, completely inseparable. The availability of vast, high-quality datasets and the sheer ability to train bigger and bigger models have been absolutely fundamental. Think about ImageNet. That dataset set the tone for how data is now treated in deep learning research. Millions of labeled images that was the fuel that allowed CNNs to learn robust visual features, or look at companies like Tesla constantly collecting environmental data as well as driving data from their cars to train their autonomous driving models. The emphasis now is on high-quality data, even using synthetic data generation to feed these massive models. They just have an insatiable appetite for information to learn complex patterns.
So it's not just the clever algorithms like backprop or self-attention, it's this triad. Brilliant algorithms fueled by massive data run on powerful hardware like GPUs.
That's a perfect summary. The algorithms are key, yes, but the fuel of data and the engine of computation are equally critical. They allowed connectionist models to scale up, to learn from the complexity of the real world at an unprecedented level, moving way beyond toy problems.
And these incredibly powerful systems are clearly changing our world, sometimes with amazing benefits, but also raising some really significant questions and challenges. That brings us to broad impact and lingering questions. Where are we seeing connectionist AI making the biggest difference today? And what are the critical issues we still need to wrestle with?
The impact is becoming widespread. In healthcare, AI can assist in diagnosing diseases, analyzing medical records, scans, helping find patterns humans might miss, even aiding in personalized treatment recommendations. In education, you have AI tutors like Conmigo offering personalized learning, adapting to each student's pace. And generative AI is helping teachers with planning, grading, creating materials. It has the potential to be a powerful tool across many sectors.
That sounds incredibly positive. Augmenting doctors, personalizing education. But of course, with such power comes responsibility and some serious societal and ethical questions we need to face.
Indeed, there are significant concerns. Job displacement is a big one, not just for repetitive tasks anymore, but potentially impacting creative fields too. Sources mention worries about AI making huge swaths of labor redundant, citing the appeal for corporations to replace labor with technology. Then there's the persistent problem of algorithmic bias. AI systems learn from human data, and if that data reflects societal biases, the AI can learn and even amplify them.
Like that example of the NLP model associating man with programmer and woman with homemaker.
Exactly, or findings suggesting Facebook's ad targeting algorithm might have violated fair housing laws by skewing who sees housing ads based on protected characteristics learned implicitly from data. These biases can have real discriminatory consequences. And we also have to consider the environmental costs. Training these huge models consumes enormous amounts of energy.
These are really profound challenges. Bias, job impacts, environmental footprint. It seems like while these systems are incredibly capable in some ways, they still have significant limitations and require very careful management and oversight.
They absolutely do. Current systems, despite their power, still lack true understanding or common sense in a human-like way. Their behavior can be brittle, unpredictable, even manipulated. Think about generating misinformation or deception. It underlines that the Connectionist legacy isn't over. It's an ongoing story. We need continued research, not just on capabilities, but on safety, ethics, alignment, ensuring AI truly benefits humanity. As the source said, we would have to do our homework, and that homework on responsible AI development and deployment is far from finished.
What a journey we've traced. From those earliest brain-inspired sparks, Hebb's rule, the perceptron, through the challenging AI winter that forced a crucial reevaluation, to the triumphant return of connectionism with PDP, deep learning, reinforcement learning. We've really seen how ideas once deemed impossible have become the bedrock of today's AI.
The Connectionist legacy truly isn't a finished chapter. It's a living testament to continuous innovation, the absolute necessity of learning from setbacks, and the surprising power of these distributed adaptive systems. It reminds us that big shifts in science often come only after periods of doubt, followed by persistent, sometimes quiet, research and a willingness to fundamentally rethink assumptions.
The implications of this ongoing evolution are just staggering. As these connectionist models keep scaling, keep demonstrating more sophisticated emergent abilities, those unexpected capabilities like planning with tree of thoughts or reasoning and acting with react, behaviors not explicitly programmed but arising from sheer complexity, what unexpected forms of intelligence might these principles unlock next? And maybe more importantly, how will we as humans adapt to these ever-evolving minds that continue to push the boundaries, challenging our very definitions of capability and intelligence? That's definitely something to ponder long after this deep dive is over. Thank you for joining us on this deep dive into the Connectionist legacy. We hope you're leaving a little more informed and maybe a lot more curious.